In this video, we'll be talking about section 9.2, primarily binomial expansions, but we'll also be talking about multinomial expansions. And I think the main reason that this section is here between 9.1 and 9.3 is that binomial expansions are a precursor to an important method that we'll use in 9.3. Also in this video, these notes, we'll hit a couple other things. Combinatoric proofs, which will use some heavy factorial work. Partitions, which is using combinations, and we'll talk about what that is. Derangements, which is a special type of permutation. And we'll return to distributions. Before we talked about distributions and used the words at least, but we did not talk about at most. And in order to do that kind of problem, we'll need to do complementary counting in combination with combinations and also with the pi method. In this picture here, we are doing binomial expansions. A binomial to the 0 power, of course anything to 0 power is 1, to the first power, second, third, and fourth power. And so this was FOILed out 4 times to get this binomial expansion. Binomial because there's 2 pieces. The coefficients in the resulting binomial expansions are called Pascal's triangle. I want to look a little bit more closely at the a plus b to the 4th power expansion. That's a plus b squared times another a plus b squared, expanding the squared factors. I'm only going to do a portion of the multiplying out, only that part which will result in 2 a's and 2 b's. So that would be like a squared, b squared, 2 a's, 2 b's, 2 a's, 2 b's, and only the 2 a's and 2 b's, leaving everything else untouched. And what you might notice is the result is the sample space of all the different ways that we can spell a word with 2 a's and 2 b's. Recalling from our previous method of the spelling method of how many ways can you arrange 2 a's and 2 b's, that's 4 total letters, 2 a's, 2 b's, and when we do the math, we get 6. 6 is the coefficient when we have 2 a's and 2 b's. Also, because there are only 2 different letters, just a's and b's, this fraction right here can also be written in a combination form. 4 things taken 2. In the same way, every single coefficient, or every number in Pascal's triangle, can as well be written in combinatoric form, in the same way as we did 4 things take 2, 4c2, and that would be on the 4th row when there are 2 of the a's or 2 of the b's. And so we can look at Pascal's triangle as starting at row 0, and remember 0 factorial is equal to 1. And also, in addition to row 0, having term 0 at the beginning of each row. So we go from 0, 1, 2, 3, 4 on the 4th row. In this first question, what's the coefficient of the x to the 8th, y to the 3rd term in the expansion of x plus y to the 11th power? We can use the combination method that we just talked about, which would be 11. Take 8 x's. It would be the same thing as 11, take 3 y's, or 11c3, and that way is the way I would do it on my calculator, using the math button, and get my answer of 165. As far as how many terms would be in the entire expansion, we saw that we start at term 0 and go all the way up to term 11. So there's 1 extra term beyond the exponent, so there would be 12 terms in the expansion. As far as what all the coefficients in the entire expansion add up to, we're going to look at a small piece of Pascal's triangle which holds the coefficients. And if we add up the coefficients in row 0, they will add to 1. Row 1 will add to 2. That's 2 to the 1st power. Row 2 adds 2 to the 2nd power. Row 3, 2 to the 3rd power. So each row, the sum of the coefficients is 2 to the exponent or that first non-1 number. And so in our case, it will be 2 to the 11th powers, which they would all add up to, and the first two numbers in the row would be 111. You should notice that a different way we could get this answer is to say that if we did the full expansion, and that would be all 12 terms, the letters x and y would make no difference in what the coefficients added up to, because these are variables. So we might as well just get rid of the x and y by making them both equal to 1. Then in each term, you'd be multiplying by powers of 1. Then you'd get 1 plus 1 to the 11th. So by just turning the letters into 1s, you get the same exact answer for what all the coefficients in the expansion add up to. That'll be important later on. We could represent the full expansion of a row with a sigma notation. R equals 0 to n. So in other words, if n is 11, 11 things taken 0 at a time, that'd be the initial term, then 11 things taken 1 at a time. And our exponent to the first factor would be the difference, so 11 minus 0, and the second one would be to the 0 power. Notice as we make our expansion with the sigma notation that we have our coefficient at the beginning of each term, that the power on the initial a value goes down by 1 each time, and the power on the subsequent b value goes up by 1 each time. But in each term, the sum of the two exponents always adds to 11, if it's an 11th power to start with. And I should have said a plus b to the 11th, not x plus y to the 11th, since we have a's and b's. In these three questions here, one of them pertains to a binomial expansion with two parts, and two of the questions are about multinomial expansions. That would have more than two parts, so in this case it's 3 parts, but it could have 5 or 6, how many ever terms would be on the inside. It would be a multinomial. We said previously that one way to think about the coefficient is to think about spelling. For instance, we got the 6 before by thinking about all the ways we could spell 2 A's and 2 B's. This time, though, we have 3 X's, 2 Y's, and 1 Z. So the spelling would be a total of 6, so 6 factorial, 3 factorial, 2 factorial, 1 factorial. But that is not using combination. We can't use the Pascal's triangle. We can't use the combination method when there is more than 2, but we can play off of that by using the spelling method, and combination in a way is a subset of spelling. In the next one, we asked about the 7th term in the expansion. Why is it not 7? Because remember, the initial term is term 0. So the 7th term would be 0, 1, 2, 3, 4, 5, 6. So 9 taken 6 at a time. Our 6 would be representative of the exponent on the 2nd term. So this number will also be here. And the remaining number is what adds it up to 9. So remember that in each term of the expansion, if you take the exponents and add them together, you must get the total exponent. Okay? That's why I knew that this had to be the expansion to the 6th power. Once I saw 3, 2, and 1, I couldn't have written the 7th power here. Notice that the coefficient comes from 3 different places. It comes from the combination 9 taken 6. It comes from the 3 to the 3rd power. It comes from the 2 to the 6th power. I have to multiply all 3 of those numbers together to get my total coefficient, and then the x's and y's just follow with their powers. To get the sum of all the coefficients in the entire expansion, I would, as I said previously, replace the x's and y's with 1, because the variables don't add to the coefficients, and so it'd be 3 times 1, 2 times 1, or 5 to the 9th. And it would be fine to leave your answer just like that instead of some monstrous number to the millions. Notice when we're talking about multinomial expansions, we cannot say something like, what is the seventh term? Yeah, we have an order of terms when it's binomial. We know we start with this to the 0 power, then this to the first power, or actually the other way around, this to the 9th power, then this to the 8th power, this to the 7th power. We have an order from Pascal's triangle, but we don't have an order for multinomial, so that's why we wouldn't say the seventh term. We would just say the term with these powers in the letters. I'm going to use my spelling technique by adding up the powers and how many x's, y's, and z's, x's, y's, and z's to get my total term figured out. Again, notice that the overall coefficient comes from both the factorial part and each individual term's coefficient being taken to a particular power. And it is possible that we have a minus in front. As far as what all of the coefficients add up to, again, I'll replace the letters with 1 in each case, and I will leave my answer just as 4 to the 7th power.